Good morning, class. We are looking at practice test number 2, module 2, covering chapters 4 and 5. Here's chapter 5, discrete probability distributions. Does this table describe probability distributions? What is the random variable, whether it's possible values, and are its values numerical? So here's the table, number of gears in 3 pairs. X represents the number of gears that can be 0, 1, 2, 3. Probability for X being 0 is given as 0.125, for 1 is 0.375, for 2 is 0.375, for 3 is 0.125. All right, here's how we know it is a probability distribution or not. The variable X, in this case, which is the number of gears in 3 pairs, namely 0, 1, 2, and 3, is a numerical random variable. So it has to be a numerical random variable, and it is. And its values describe probabilities. So that's one element, one characteristic that works. The second characteristic, summation of P of X. If we add this column, they must add up to 1. So 0.125, 0.375, 0.375, 0.125. We add them up. Do we get 1? Yes. One thing I want to mention here. The only time you may not get 1 and still is fine if it's close to 1 due to round of error, meaning the result is 1 point, a lot of zeros, and then 1, 1.000001, or 0 point many nines, 0.9999. That's due to round of error, so it's practically 1. Otherwise, it has to be identical to 1. The next one is that each probability must be between 0 and 1. Each value of P of X is between 0 and 1, as you can see the numbers. And this is another important fact. So it has to be a numerical random variable. It is. The sum of probability must be 1, and each probability must be between 0 and 1, meaning can't be negative, can't be larger than 1. In a game, you pay 60 cents to select a 4-digit number. If you win by selecting the correct 4-digit number, you collect $3,000. How many different selections are possible? Well, we have 10 digits from 0 to 9. So n, the number of digits, is 10 because we go from 0 to 9. So we have 10 possible numbers in 4 spots. We have 4 places. And each one has 10 possibility. Therefore, the answer is 10 to the power of 4, or 10,000. Numbers can repeat. There is no limits. There is no restrictions. What is the probability of winning? By definition, probability of winning is n of winning over n of s. There is only one way to win out of 10,000. 1 over 10,000. If you win, what is your net profit? Well, you collect $3,000. You've paid 60 cents, subtract from it. So money gain minus investment or cost, and that gives us $2,999.40. Write the probability distribution of a net profit. So you set up a table. In short, for a discrete random variable, a probability distribution is simply a table of X and P of X. So X and P of X. But just to make sure we understand what's happening, number of 3,000 winners, how many are going to win 3,000? Only one. The total is 10,000. Everybody else is going to lose. So it's 1 here, 9,999 here, 10,000 total here. What is the net gain for the winner? $2,999.40. What about the loser? Everybody loses 60 cents. So negative $0.6. What is the probability? For each case is the number over the total. The number would be 1 here over 10,000. The number would be 9,999 over 10,000. That is called the probability distribution table. We're going to continue with the same question. The next part is asking to find the expected value and interpolate. Number one, this table comes from the previous page. Number two, reminding you of the formulas for discrete probability. Mu is summation of x p of x. Sigma squared variance. Sigma squared is the variance. Summation of x squared p of x minus mu quantity squared, or summation of x minus mu quantity squared times p of x. So to calculate this, we are going to go with this table and multiply this one by this one. Therefore, we are going to create x times p of x. And later on, we're going to use this format. Therefore, we're going to need x squared p of x. So what happens here? X p of x, multiply these two numbers, put it here. Multiply these two numbers, including the sign, put it here. So when we multiply these two, we get 0.29994. When we multiply these two, we get negative 0.59994. We are going to add them up, and that becomes mu. When you add up these two numbers, you get negative 0.3. So that is the expected value. So mu, or summation of x p of x, is negative 0.3. So meaning 30 cents in essence. Again, we did this table for the sake of calculation. Now, how do we calculate this x squared p of x? Raise this to the power of 2 multiplied by this, put it here. Raise this to the power of 2 becomes positive times this, put it here. And now, according to this formula, add them up. And now if I want to find the variance, I use this formula. And if I want a standard deviation, I use the same formula. I take a root, square root of that. We are interested in sigma, standard deviation. So square root of this number minus mu, which is this number quantity squared. So square root of 900 from this column minus mu is negative 0.3 from the previous column, quantity squared. And you come up with the answer. It is almost 900 because 0.3 squared is 0.09. So you take a root of that and you get 29.9985, almost 30. What is the meaning of that? This is what's important. The interpretation of this is more important than anything else. What does it mean? So what? So on average, a player, all players, a player loses $0.3, meaning 30 cents per ticket, with standard deviation of $30 on the average. That's the concept of expected value. A pharmaceutical company receives large shipments of aspirin tablets. The acceptance sampling plan is to randomly select and test 24 tablets. The entire shipment is accepted if at most 2 tablets do not meet the required specifications. If a particular shipment of thousands of aspirin tablets actually has a 5.0% rate of defects, what is the probability that this whole shipment will be accepted? Let's discuss BD, short for binomial distribution, which is known if N and P probability of success, they call it, is given. So this is a BD, short for binomial distribution. If you claim something to be a binomial distribution, you must come up with 2 numbers. N is 24. Probability of success. It's known as probability of success, doesn't necessarily mean a positive or negative thing. So 5% rate of defect, because you're looking to find defects, that is the probability 0.05. In which case, we use the following formulas. P of x is n factorial over x factorial and minus x factorial. If you recall, this is the combination of n choose x. P to the power of x, q to the power of n minus x, where mu is n times p for binomial distribution. Sigma is square root of npq, and q is 1 minus p, the complementary. And so let's just remind you what is a binomial experiment. Binomial experiment and probability distribution properties. We have n identical, that means fixed number of trials, each repetition of the experiment. Each has only 2 categories of outcomes. Probability stays constant, independent trials. In short, you have n identical trials with 2 outcomes, only 2. And of course, all trials must be independent with a fixed probability. Probability for an event does not change from one to the next stage. So the formula is this. We are going to use p equal to 0.05. Therefore, q is 1 minus that, which is 0.95. And we're going to plug in, replacing the n with 24, p with 0.05, q with 0.95. So this would be the general formula. Going back to the question, what is the probability that this whole shipment will be accepted? Remember, the entire shipment is accepted if at most 2 tablets do not meet the required specifications. So probability of x less than or equal to 2. At most 2. This means at most 2. Which means into this formula, we replace the x with 0, then 1, then 2, and we add them up. We want probability of x equals 0 plus probability of x equals 1 plus probability of x equals 2. You could do it by hand. It is doable, and you come up with the answer. However, if you understand the concept, you can use the calculator as follows. For example, if you want to use TI calculator, binomial distribution, second variables, binomial PDF, if you enter NPX and enter, it gives you the probability for each case. You replace the x with 0, 1, 2, and so forth. And if you just don't write x, it gives you all the probabilities from 0 to n. Instead of a PDF, if you use CDF, cumulative distribution, it adds up all those probabilities. How does it add up? From 0 to this number that you put, x. Therefore, we are going to put the trial's binomial CDF. The trial N is 24, P is 0.05, X value is 2. So that gives us this probability. CDF 24 0.052. And the answer is this. As you can see, they are fine. Of course, as far as number of decimals, and I can't emphasize this enough, if they didn't tell you anything, you have to write all of these decimals. Assuming we are fine with 4 decimals, 0 is the one that is interested. We are interested in. Next to this 5 goes to 1. So you do the rounding accordingly. It is known that 70% of managers of all companies suffer from job-related stress. What is the probability that in a sample of 20 managers, exactly 8 suffer from job-related? So we are dealing with a binomial distribution because there are only 2 outcomes. Either there's managers that are suffering from job stress or not. So it makes it 2 outcomes and they are independent. So N is 20 and P is 70% or 0.7. So BD, or short for binomial distribution, N is 20, P is 0.7. Again, reminding you of those formulas. In this case, P is 0.7 and Q becomes 1 minus that, or 0.3. Therefore, P of X, we use this formula, replacing the N with number 20, the P with 0.7, Q with 0.3. Exactly 8. We are going to replace the X with number 8. So you do the math, or you can put this into a calculator as follows. Binomial PDF, N is 20, the number of trials. P is 0.7 or 70%. X is 8. And the result is what you have here. Let's say, again, if they just ask you this question, you have to write all of this. But if you want to round it, for example, if I want to stop here, next to it is 8, I take this up 1 notch and make it 3. So do the rounding accordingly. Okay. This is the result. Be very careful with your rounding, everybody. I'm going to continue with the same question, part B of the same question. This is the same question. This is the information from the previous page. We are continuing. Part B, at most, 8 suffer from job-related stress. That means probability of X less than or equal to 8. That means probability of X is 0, 1, all the way to 8. That means add up 0 to 8. And obviously, you don't want to put 0 in here, calculated 1, 2, and 8. You can use a calculator for that. Okay. And to do so, we are going to use CDF, binomial CDF. N is 20, P is 0.7, X value is 8. But pay attention, this is CDF, cumulative. Add them up. And it gives you this number. And again, if we want to stop here, next to the 6, we take it up 1 notch. Notice 1. Next to the 6 changes to 2. At least 9 suffer from job-related stress. That means probability of X larger than or equal to 9, meaning probability of X equals 9 plus probability of X equals 10, 11, 12, all the way to 20. And the way to calculate this, it's easier to write it as 1 minus P of x less than or equal to 8. First of all, we have it from the previous one, but even if we don't, we can put it in here, calculate this, subtract it from 1. So this is how you do the calculation. Be very careful. Probability of x larger than or equal to 9 is the same as 1 minus probability of x less than or equal to 8. This is complementary event. So 1 minus this number. And I truncated at this number. Again, please pay attention to the rounding. If there is no rounding, you have to go with all those digits. So 0.99486. Same question, we want to find the expected value. Expected value, mu is n times p. 20 times 0.7, 14. So that means among 20, we expect 70% of them, or 14 on the average, to suffer from stress. That's the concept. What about the standard deviation? Find the standard deviation. Sigma is square root of npq, which means multiply 20 by 0.7 by 0.3. That becomes sigma squared, which is 4.2. Take a root of that. Remember, this is variance. Square root of that is standard deviation, sigma standard deviation for the population 2.05. Again, as far as the number of decimals, normally they tell you, if not, this is not good enough. You have to put a lot more decimals. I emphasize this because I've noticed students sometimes make a mistake in that regards, and therefore they miss a few points here and there. All right. Would it be unusual to claim that 7 managers from this sample suffer from job-related stress? I hope you remember the mu plus minus 2 sigma, right? The range rule of thumb. So anywhere in this vicinity is usual. Otherwise, it's unusual if it's outside. So mu minus 2 sigma and mu plus 2 sigma has to be calculated. Mu minus 2 sigma, mu is 14 minus 2 times 2.05, and then 14 plus 2 times 2.05, and we get 9.9 and 18.1, meaning any number less than this or any number larger than this would be unusual. 7 is outside the norm. 7 is not an element of this. So again, in between is usual. This is in set theory. It says not an element. This is red, not an element of this interval. 7 is outside this interval, therefore it's considered unusual. Find the probability of a couple having at least one girl among 3 children. Generally speaking, we know that probability of G and B, girls and boys, is the same as 1/2. And we have this method, probability of at least one is 1 minus probability of none. Now, it so happened that it's the same 1/2 in both cases. but it's important not to mix them up if they are not the same, because in some cases, if the probability is not identical, you should know which one is which. And I'm going to explain that in a moment. So this is 1 minus probability of none. Probability of none, no girls, that means probability of all boys. That means probability of a boy, 1/2 to the power of 3. This means all boys. So probability of none, at least one girl, none, no girls. That means this means all boys. Let me just all boys. That's the meaning of it. 1 minus 1/2 cubed, which is 1/8. So 1 minus 1/8 is 7/8. I'm assuming we have no problem with decimals and fractions. Here's method 2, binomial distribution. N is 3. Probability is 0.5. Please understand, it so happened probability is the same for both of them, but this is considered probability of success. What we want in this case is to deal with a, a, a child born to be a girl. So probability of at least one, x must be larger than or equal to 1. P and Q are the same, happen to be 1/2. X is 1, 2, 3 because we have total of 3. And so probability of 1 plus probability of 2 plus probability of 3. And again, it's easier to write it as 1 minus probability of 0 because this one, 3 of them has to be calculated. This one, only this one is calculated, subtracted from 1. And we use the BD or binomial distribution because there are only 2 outcomes with P and Q being the same, which is 1/2, and N is 3. So N is 3. So into this formula, we put 3 factor over x factorial times 3 minus x factorial times 0.5 to the power of x times 0.5 to the power of 3 minus x. Please understand this must be the probability of having a girl, and this must be the probability of having a boy. They happen to be equal, but let's say this was 0.6 and this was 0.4. Don't mix them up. And so we write it in this fashion, and I want it. Of course, 0.5 to the power of 0, anything to the power of 0 is 1. Okay, 3 factorial and 3 factorial cancel each other is 1. So it's 0.5 cubed or 1/2 cubed, which is the same as 1/8, by the way. What I want you to know, we should use P of B as 1 minus P of G for P of 0. It's important to know this is P of G, this is P of B. They happen to be the same. And I mentioned that because what if they are not the same? You know which one is which. Don't mix them up. Again, just for the sake of argument, assuming probability of having a girl is 0.6, then probability of having a boy is 0.4. So this would be 0.6, this would be 0.4. So we have 1 minus 0.5 cubed, 0.5 cubed is 0.125, and we get the same answer. And this is the second method I wanted to mention. If an alarm clock has a 0.9 or 90% probability of working on any given morning, what is the probability that it will not work? And by the way, this is the concept of quality control. And 0.9 is actually pretty bad, probability of 90% for an alarm clock to work, but in case. So complementary event says 1 minus that. So probability of working, let's say W for working is 0.9. Probability of W naught, the complement. This is A naught or A complement. It's 1 minus PA. That's how you read it. 1 minus probability of working, which is 10% or 0.1. So what is the probability that 2 such alarm clocks will not work? This is what I mean by probability, understanding the probability and quality control. So it's bad that only 90% probability for an alarm clock. That means 10% probability that it won't work. But what if we have 2 of it? Probability of W1, the first one working, is probability of an alarm working. Probability of W1 not, probability of an alarm not working. That's how we are going to define that. So the probability that they won't work because they're independent, one has got nothing to do with the other unless for some reason they are related. For example, if you use the same plug for an alarm clock for both of them and the power outage, then they become dependent. Otherwise, it's independent. So we are going to multiply the two, and each one has a probability of 10% or 0.1 of not working, and the product is 0.01, meaning there's a 10% chance that one of them won't work. However, as independent characters, there's only 1% chance that it's not going to work. Okay, there is 1% probability that two such alarm clocks will not work, and they use this in industry. Okay, that's why, for example, the jet engines work independently. So if one fails, others don't. We're going to continue with the same question. Part C of the same question. What is the probability of being awakened if you have two such alarm clocks? So we already have this from the previous page. And so one easy way, method one, probability of being awakened is 1 minus probability of not being awakened. That means we are assuming we are waking up to the alarm, by the way. Okay, so 1 minus 0.01 or 0.99. There's a 99% chance of waking up. Again, assumption, we wake up to our alarm clock. Here's the second method, addition method. Probability of A union B is probability of A plus probability of B minus probability of A intersection B. Each one has a probability of 0.9. We use this formula, probability of W1, which is 0.9, probability of W2, which is 0.9 minus this. Remember, it's 0.9 times 0.9. It's the working, okay? So this becomes 1.8. This becomes 0.81. And we get the same 0.99. Here's the third method, using the binomial distribution. N is 2, P, the probability of working is 0.9. And in this case, N is 2, P is 0.9, Q is 1 minus that, or 0.1. So we replace the N with 2, we replace the P with 0.9, Q with 0.1. I hope you remember when I was discussing boys and girls, I mentioned if the two are different, you know which one is which. So probability of X larger than or equal to 1, as long as one of them works. So that's why you say probability of X larger than or equal to 1. And it's easier to say 1 minus P of 0 for the sake of calculation. Otherwise, we have to calculate probably in here. Goes X equals 1 plus X equals 2, and then you add them up. But if we calculate this one, subtract it from 1. And this is 1, this is 1, this is 0.1 quantity squared, which makes it 0.01, and the difference is 0.9. And there are 3 different ways of approaching this, everybody. Last question. During an NFL season, there were 256 games played with 1,307 touchdowns scored. We are going to use Poisson distribution. What was the mean number of touchdowns, TD for short, scored in each game during the season? And we're going to round this to the nearest tenth of a thousand. So 4 decimals. So first, let's remind everybody of Poisson distribution. Poisson distribution. The probability of the event occurring X times over an interval. The interval can be time, distance, area, volume, or some similar unit, is given by P of X equals mu to the power of X, e to the power minus mu over X factorial, where e is the base of a natural log. 2.71828 continues indefinitely. It's an irrational number. Mu is mean number of occurrences of the event in the intervals. And the parameters mu and sigma, both of them are equal to square root of mu. So the mean number of touchdowns is the total number of touchdowns, which in this case is 1,307, over the total number of games, which in this case is 256 games. And that gives us this number, and we are going to go with 4 decimals. So 1, 2, 3, 4, 4. Next to it is 6, goes up to 5. The formula used for Poisson distribution, P of x is mu to the power of x, e to the power minus mu over x factorial. Well, replace the mu with this number. By the way, e is not missing. You put it as e, and the calculator can use the e. And instead of 2.71828, it uses a lot more decimals, okay? On January 10, 2010, the Green Bay Packers and Arizona Cardinals played a playoff game in which there were 13 touchdowns scored. What is the probability that a random game would have that many or more touchdowns? We want the probability of x is greater than or equal to 13, which means probability of x equals 13 plus probability of x equals 14 all the way to the last one, okay? Infinity in essence, how many, you know, as the Poisson distribution is concerned. So 1 minus probability of x less than or equal to 12. So we calculate this one, we subtract it from 1. And to calculate this one, that means into this formula, you put x equals 1, 2, 3, and so on, and you calculate them, including 0, by the way, and add them up. Or you can use a technology. It's very similar to binomial distribution, second variables, Poisson PDF, mu, or lambda or x. This depends on, you know, what you're using. For example, let me show you right here. When you use Poisson CDF, again, we use PDF or CDF. We're going to use CDF. Here's the number. Notice I used with a lot more decimals here. The x value is 12 and paste. They use lambda, okay? It's important to know mu or lambda. Mu or lambda is the same thing. In many texts, they use lambda, Greek rather. And it gives you this number. So therefore, 1 minus that is the answer. 1 minus this number. And again, there's a lot of decimals. And then since they want 4 decimals, you have 1, 2, 3, 4. Only this number, 0.0024 is the answer. All right, we're going to continue with the same question. This is the information from the previous page. We want to fill up the table. The first column lists the number of touchdowns, 0, 1, 2, 3, and so forth. This is filled in already. The second column is for the predicted probability. We're going to calculate the probability and put it here. That the game chosen at random will have that many touchdown scores. Calculate these values, round them to the to 4 decimals. Okay, nearest 10th of 1,000. The third column is for your best prediction about the number of games during the season that had that many touchdowns, and we have to round it to the nearest whole number. So basically, here's the formula. For this one, plug in 0. Now, you can use this formula, plug in 0, or you may recognize this is 1, e to this power only. See, e to this power, because this is 1, any number to the power of 0 is 1, 0 factor is 1. And if you go with Poisson PDF, okay, that gives you the same value. I want you to see that's the same value. that we're going to put here. You see that? This number or this number. Now, it says predicted number of games. We will have to multiply by, see, probability column number of games, or 256. So we have to multiply this one by 256. That is the probability that happens. So times the 256, 1.55, and we round it. So this, first of all, I wrote it just the way it is here. Secondly, they want 4 decimals, so we stop at 0 and we change it to 1. Okay, but again, I'm putting the number here, 4 decimals. For the right side, we're going to multiply by 4, we get this number. Rounding it to the whole number, I change it to 2. So this is the answer. We change it to 2 because we want whole number. Now the next one is 1. And that is the number that I mentioned, 1.55. 1.552, and rounding it up becomes 2 because it's 1.5. Okay, because of this 5, this changes to 2. Here's the next number. Okay, so for example, for 1, if we calculate it, we get this number. So this number goes here. Again, we want with 4 decimals, 0.0309. Next to this 5 goes up. So this changes to 0, this changes to 1. 0.0310, that goes here. We multiply this number by 256 and we put it here. 7.9, whatever. We change it to 8. This is this number. This is being multiplied by 8 and rounded to a whole number. The next one here, into this formula, okay, into this formula, x is 2. If you put, so we got 0 and 1. Now if you put 2 here, we get this number, 0.0590, and we stop at here because next to it is 2, it doesn't change, so it goes in here. What about this number? We multiply this by 256, we get 20.23, and we round it to the whole number to 20. So this is 0.079, and this is 20.23. We change it to 20 because we want a whole number.